Hey guys, thanks for tuning in. In this video, we're going to introduce spherical coordinates. All right, so to try to build our spherical coordinate system, we're going to start by trying to parameterize a sphere. This is useful for a couple reasons. One is remember that if you can parameterize a region, you could probably integrate over it. But also, once we can parameterize a sphere, we could use that knowledge to try to build out a spherical coordinate system. And all spherical coordinates will be are a higher dimensional three-dimensional analog of polar coordinates. There's basically two ways of lifting up two-dimensional polar coordinates into three-dimensional space. The first one you already learned last chapter, but we'll reiterate it in this chapter anyway. That'll be cylindrical coordinates. And the other one is what we're going to talk about right now, spherical coordinates. Now, since a sphere lives in three-dimensional space, we could probably lock down the parameterization for a sphere by looking at three cross-sections of our sphere. We're going to take three cross-sections that pass through the origin for a sphere centered at the origin, and we'll look at the intersection of our sphere with the xy plane, the intersection of our sphere with the xz plane, and the intersection of our sphere with the yz plane. And once I can get all three of those circular cross sections, I could try to join them together to get the full parameterization for our sphere. So we'll start with our cross section that intersects the xy plane, and we get that by placing a cosine in the x position and a sine in the y position, and then we have obviously a 0 in the z position. So we have r cosine t comma r sine t comma 0. Similarly, we can get our cross-section of our sphere with the zy plane. So I'll put a cosine into the z slot and a sine into the y slot and a 0 in the x position. And then finally, we can also get our xz cross-section of our sphere. And we do that by putting cosine into the z slot, sine into the x position, and then 0 here in the y position. Now I want to join all three of these together. So the way that I'm going to do that is I'm going to kind of just mush together the pictures, and I'm going to mush together these three cross sections, and I'll just take each relevant part. So for example, you can see here I've got an r cosine t and an r sine s. When I join those together, I'm just going to take each of the pieces that I need. So I need an r, because each of them have an r. I need a cosine of t, and I need a sine of s. So watch, I'm going to do some mushing here. Just let that run for a second. And there it is. I just took all of the relevant pieces from each of the coordinates. And so I've got an r cosine s sine s. I've got an r sine t sine s, and I have an r cosine s, and I also mushed together the pictures. And you can see that it looks like those three cross sections exist on a sphere living in 3D. So I can try to fill out the rest of the sphere by allowing r, s, and t to vary as appropriate. So here it is. This is our parameterization of a sphere. We've got r cosine t sine s, r sine t sine s, r cosine s. Now, a common question that I get is, hey, on the previous slide, you were picking where to put like your cosines and your sines, and why were you putting them where you were and picking the variables that you were? The answer is there's actually more than one way to parameterize a sphere in three-dimensional space. So I made some somewhat arbitrary choices, and they seemed arbitrary at the time when I was doing that on the previous slide, but this gives us our standard parameterization for a sphere that most people use. So that's pretty much the answer to that question. Is there a different way that I could have assigned where to put the sines and the cosines and gotten an equally valid parameterization for a sphere? Yes, there certainly is. But this is the parameterization for a sphere that's in your textbook. And this is the parameterization for a sphere that you see from most sources. So that's the one we're going with. So that's why I made the particular choices I did about, why did I put the cosine of t here and the sine of t here? Why didn't I swap those, for example? And so there would have been other ways to go about it. Another thing to note is it is worth memorizing the parameterization for a sphere. You're going to use it a lot in the remaining chapters in this course, so it's something that is worth putting on a flashcard and committing to memory. I will help you guys try to work through how to memorize this without having to put it on a flashcard. But whatever method you choose, you do need that committed to memory. And then the other thing that you do need to remember is, this is interesting, t varies from 0 to 2 pi, while s only varies from 0 to pi. And we'll talk more about this, especially in my next video, about why we are letting t do a full rotation from 0 to 2 pi, while s is restricted from 0 to pi. But beyond just understanding it, it is something, again, that will have to be committed to memory, because it's going to be an important part of integrating over this region. So here's how I memorize this. So I think about my 3 cross sections. So first of all, I think about my cross section on the xy plane. So that's going to be r cosine t, r sine t. That's my circular cross section of my sphere on the xy plane. So it also looks just like the unit circle, right? Or a circle of radius r. So r cosine t, r sine t is pretty familiar. Now I'm going to do the same thing for my other 2 cross sections, but instead of building from left to right like we see here, my other cross sections I'm going to build from right to left. So now from the z slot, I have an r cosine s and an r sine s. That's going to be my cross section on the xz plane. And similarly, I've got r cosine s in the z slot, r sine s in the y slot, and that gives me my cross section on the yz plane. And again, like I was mentioning a couple seconds ago, there are other ways of parameterizing a sphere in 3-dimensional space, and that would involve making different choices about where you're placing your cosines and your sines. This is the standard one, and the reason it is as it is, we kind of want to think about our sphere starting from the North Pole and kind of building down from there. And so we're rotating down from the z-axis, the North Pole of our sphere. So there are other ways of doing it, but it would start building that sphere from a different point in 3D space, which might be a little less intuitive to most people. All right, so now that we have our parameterization of a sphere, remember that if you can parameterize a region, that's a map between your region and in 3D space, an RST rectangular prism. So we have just determined a map between a sphere in XYZ space and a rectangular prism in RST space. So we have our mapping here on the screen. If you have a parameterization of a region, you also have a mapping between RST space and XYZ space. And we can now use this to integrate over our region as well. So we've got a spherical coordinate system, we have a parameterization for a sphere, we have the ability to get a volume conversion factor, and we're also going to have the ability to compute triple integrals over using spherical coordinates. So when someone talks about spherical coordinates, here are instead of having an x, a y, and a z with rectangular coordinates, we have an r, s, and t. And one important part of this course is understanding what each of these represent. So s is going to be a rotation down from the positive z-axis. So how many degrees am I rotating down from the positive z-axis? R and t are a little bit more familiar. R is just our distance from the origin to whatever point we're trying to get to, and t is a rotation on the xy plane. Well, that's the same t that you're familiar with from polar coordinates, right? This is the same as the t in 2D polar coordinates, because in 2-dimensional polar coordinates, it's the same deal, right? T is a rotation starting at the positive branch of the x-axis, right? The positive branch of the x-axis, and then rotating in the counterclockwise direction towards the positive branch of the y-axis, and then you have however many radians you're rotating. So r is familiar, it's a distance from the origin. T is familiar, it's a rotation on the xy plane, starting at the positive branch of the x-axis and moving towards the positive branch of the y-axis. The only parameter here that is a little bit new is this s, and we call s the zenith angle, which is a nice convenient I mean, this is just pure luck that this happened, but zenith starts with Z, and it's a rotation down from the positive Z axis from the North Pole. And then T is called the azimuth angle, and that's our rotation on the XY plane. So zenith and azimuth both have a very interesting etymology. I don't want to spend too long on this, but these words are hundreds of years old, and they come from Arabic. And it comes from an era when people were trying to navigate the globe, taking ships, trying to go very long distances. And so zenith is Arabic for over one's head. And that makes sense because the zenith angle, you're starting from the positive branch of the z-axis, and you are rotating down s radians from the positive z-axis. And then in contrast, we have azimuth is Arabic for the way, because it's the way that you are pointing on the xy plane, which when you're on Earth, any point you're standing on Earth is approximated by an xy plane at that point. And so it's really, how many radians t you're rotating from the positive branch of the x-axis towards the positive branch of the y-axis. And so these words come from when we were trying to navigate using the stars, right? And you can actually see where these words kind of spread through from Arabic to Old Spanish, then from Old Spanish to Medieval Latin, then from Medieval Latin to Middle French, then from Middle French to Middle English, and then all the way into Modern English. Pretty interesting. All right, so if we are going to use the parameterization for a sphere as a coordinate system, spherical coordinates, then we better find a volume conversion factor that allows us to integrate using this parameterization. So we already know how to compute volume conversion factors. I'm not going to go into every detail here. I'll give you guys the setup. And then if you would like to compute that 3x3 determinant, go for it. It is a good exercise in making sure you understand the material, but you get r squared sine of s. And just like you need to memorize the parameterization, the standard parameterization for a sphere, you are also going to have to memorize the volume conversion factor for spherical coordinates. This is a freebie unless you are specifically told you have to derive it. So on a quiz, on the final exam for the course, whatever, you're allowed to use r squared sine of s for free unless the problem specifically says you must derive this volume conversion factor, which is not going to come up very often. All right, so to summarize, we now have a mapping between an RST rectangular prism and an XYZ sphere, and that's really, it's just a parameterization for a sphere in XYZ space. If we could parameterize a sphere, we could probably integrate over it. And if we could parameterize a sphere, we have a mapping between an RST rectangular prism and an XYZ sphere. And we also have a volume conversion factor to go with it. So now we could try to crunch some numbers on some interesting problems. So in this problem, we want to find the volume of the solid described by x squared plus y squared plus z squared is less than or equal to 9 using a triple integral. That might sound more complicated than it really is. We're just being asked for the volume of a sphere of radius 3. And you guys already know that 4/3 pi r cubed is going to do the trick. So technically this problem doesn't need calculus, but you've seen how I like to teach and introduce this sort of material. I like to compute a simple example first, and then we'll build up to some more interesting examples. So here's a problem that we could have done using 4/3 pi r cubed, but let's try out our new calculus skills. So first of all, computing this as an XYZ space integral, not great. Can it be done? You bet, but it would not be fun to do by hand, and you would need some more integration knowledge than you currently have. You would need a larger top 20 integrals table in order to do this. All right, so we can do this in RST space, and it's a much more pleasant calculation. So now we know that R goes from 0 to 3 because it's a sphere of radius 3. So we want to integrate all the way from r equals 0 all the way out to r equals 3. And then s and t, these need to be remembered here. If we're integrating over an entire sphere, s needs to go from 0 to pi, and t gets a full rotation on the xy plane of 0 to 2 pi. So those are our limits of integration. The most common mistake to make here is to accidentally put a 2 pi in for our ds integral. That will give you double the result you're looking for. So don't accidentally double that s top. Leave that as 0 to pi. Finally, I do have absolute value bars here because technically you're triple integrating the absolute value of the volume conversion factor. But what I want you to remember is that r squared is always positive. And so the only way that this volume conversion factor could go negative is if sine of s were to go negative. But when s varies from 0 to pi, we're never going to end up with anything negative there. So as long as we have the correct bounds for our s low and our s top, we actually don't need these absolute value bars. So now let's try to compute it. So I can ignore the absolute value bars here. And the integral of r squared sine of s with respect to r is r cubed over 3 sine of s. Then I'll plug in r equals 3 and r equals 0, and I'll subtract. Fundamental theorem of calculus here. You end up with 9 sine of s. Now we have a double integral, so we're going to integrate 9 sine of s with respect to s. We get negative 9 cosine of s. Plug in s equals pi and s equals 0, then subtract. Fundamental theorem of calculus again. Now you just need to know a little bit of your unit circle. And now we have the single integral of 18 dt. And you guys know how to go straight to your answer there. That's 36 pi. All right, so in the previous example, we just found basically the volume of a sphere, right? We did 4/3 pi r cubed, but we used the triple integral to get that result. In this case, we are not able to use 4/3 pi r cubed. We're going to find a triple integral that has an integrand that is not equal to 1, so we are going to have something that is not a volume calculation anymore. So be careful right there. In this example 2, we have added an integrand, and we are unable to just use a geometry formula. All right, so at this point, calculus is necessary because we don't have any other way of doing this. But I do want to remind you that just because we have to use calculus and it's going to be a more complicated calculation doesn't mean that it has to be a very difficult calculation. Remember that x squared plus y squared plus z squared is going to equal r squared. Because we're trying to imagine r varying. Essentially what we're doing is we're computing this integral for an r that is growing from 0 to 3. And so this x squared plus y squared plus z squared is going to be equal r squared. So we could take our triple integral in xyz space, and we could rewrite it as a triple integral in rst space. Now, x squared plus y squared plus z squared is going to equal r squared. There's another way of coming up with this, by the way. You could do this algebraically. You could plug in x of rst for x. You could plug in y of rst for y, and z of rst in for z, and you're going to get an expression in terms of r's and s's and t's, and you're going to end up with two times in a row, you're going to end up using the Pythagorean identity, and everything will squish down to r squared. In my mind, it's easier just to remember that x squared plus y squared plus z squared in spherical coordinates will always equal r squared. So we can always plug in r squared here. Then we also need our volume conversion factor for spherical coordinates, which we now have memorized is r squared sine of s. And that's going to be the setup that we're going to try to integrate on the next slide. I'm out of space here, so on the next slide, I'll have a chance to unpack that a little bit. I do want to do some brief error analysis, though. The common mistake that I see is I'll see students who say, oh, x squared plus y squared plus z squared is equal to 9. So instead of putting r squared there, they'll put in 9. That's not correct, because x squared plus y squared plus z squared equals 9 is the outer skin of this region, right? That's the outer skin, the surface that bounds this solid region. And we're not integrating over this skin. we're integrating for all of our R values that radiate out and fill out all of this volume. And so you can't put 9 there. You need to leave it as r squared. Now we can multiply r squared and r squared to make r to the fourth, and this will be the triple integral we'll compute on the next slide. All right, so here's our setup from the previous slide, and now it's just using the fundamental theorem of calculus 3 times in a row, right? So the antiderivative of r to the fourth with respect to r is r to the fifth over 5. Plug in r equals 3 and r equals 0. There we go. You could pull out any constants as you start accumulating them. So we just have a sine of s left over inside the now double integral. Now we're going to take the integral of sine of s with respect to s, and we get negative cosine of s. Plug in s equals pi and s equals 0. And at this point, we know that our answer is just going to be 243 over 5 times 4 pi, which is 972 pi over 5. This is not a volume calculation, so you don't want to say that the volume of the sphere is 972 pi over 5. It's not. We found the volume on the previous example. If you'd like to, though, you could think of this as a density function. And in that case, you could say that the mass of the sphere is 972 pi over 5. At least poetically speaking, the mass of the sphere is 972 pi over 5. In that case, you would think of this sphere being made out of a material that is less dense near the origin and gets denser and denser as you move away from the origin. And then this would be its quote-unquote mass. But really, this is just an abstract calculation because we weren't told that this integrand represents mass. All right, guys, so I hope this was a helpful intro video. In my future videos, we'll be looking at some more exploration with how spherical coordinates work, and then we'll talk about cylindrical coordinates and spherical coordinates and kind of switching back and forth between the two.